or false? If A is a triangular matrix, the determinant of A is the sum of the entries in the main diagonal of A. False. What is it really? The product. True or false? If A is the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, the 3 by 3 matrix, then capital A sub 2, 2 is 1, 3, 7, 9. True, yeah. So capital A 2, 2 means we delete row 2 and column 2. So we just get rid of this and we get rid of this. And what's left is the 2 by 2 matrix 1, 7, 3, 9. So that one is true. And if A is the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, then entry 3, 2 is 6. That means the entry in row 3, column 2. Because it's that 3 and 2 stands for row 3, column 2. Third row, second column. Okay, that was a tough quiz to write because there's a lot of stuff in this section, but it's really computation and notation heavy. So I'll go through some of it in my notes. I tried to sort of like translate everything from the book's notation into just words. Hopefully it'll be easier. So today we're learning how to compute determinants of square matrices. We already know how to do it for a 2 by 2, but we can do it for larger matrices also. And then we're going to investigate some properties of determinants. All right, so we have an easy formula to calculate the inverse of a 2 by 2 matrix, right? It was this A inverse is 1 over AD minus BC times this matrix where you switch around the entries. Okay. That formula comes from setting up the augmented matrix ABCD with the 2 by 2 identity and row reducing. So it's just what you get when you do that. And we call this quantity, this AD minus BC, that's an important quantity. We call it the determinant. And when the determinant is 0, the matrix is not invertible because you can't put a 0 in a denominator, right? That just wouldn't make any sense. So when the determinant is 0, there is no inverse matrix. We could similarly derive formulas for the inverses of larger square matrices, right? I could just take A, B, C, D, E, F, G, H, I, augmented it with the 3 by 3 identity and row reduce. And I would come up with some kind of formula like this one. Right? But the formulas get unwieldy very quickly, right? They get like really big and messy, and it's not worth it to use a formula. Instead, you just do it every time, right? You just augment whatever matrix you have with the identity matrix, you row reduce and find the inverse if it exists. But row reducing a large matrix takes a lot of time and effort, whether it's done by you or a computer, right? It will take your calculator can do maybe a 5 by 5 and it doesn't seem like it takes that long, but in the computing world, a 25 by 25 matrix isn't even considered big, and doing the row reductions on that would take a long time. So it would be nice to know ahead of time if our effort spent row reducing a matrix was going to pay off, if we were actually going to get an inverse. So a determinant is something that can tell us whether or not that inverse exists. Square matrices larger than 2 by 2 also have a determinant. Tells us if the matrix is invertible before we waste time and effort row reducing. And it's the same rule. When the determinant is 0, there's no inverse. So the methods available for computing determinants all come from row reducing the augmented matrix. And because the matrix A has to row reduce into the identity matrix, certain quantities have to be non-zero to avoid losing those ones on the diagonal, right? Those things can't ever become zeros. So when you're doing your row reducing, certain things have to not be 0 in order to not knock out those ones. So the text actually derives for a 3x3 matrix. It does the row reducing and shows you what quantity has to be non-zero. This is the result. I won't derive it for you. You can read it if you want. But we have this 3x3 matrix. And instead of using A, B, C, D, E, F, G, H, I, after our 2x2, we just use these little subscripts that tell you row, column. So the determinant of that 3x3 matrix is the entry in the first row, first column, times the determinant of what's left when you delete the first row and the first column from matrix A. So we call that A11. So this is little a11 times big A11 minus little a12 times big A12, right? The matrix you get when you delete row 1, column 2. The row and column that contains the first factor in this product. And then A13, which is the third entry of row 1 times capital A13, the matrix you get when you delete row 1, column 3 from matrix A. Yes, so these guys all come from the first row of matrix A. Yep. So notice that the signs are alternating. We have a positive term, a negative term, a positive term. Notice that the first factor in each term is an entry from across the first row of A. So that's what you just pointed out. So good job, you noticed it. And then when the first factor of the term is A1 something, right? The second factor is the determinant of capital A1 same something, right? And you can actually use the entries from any row or any column as these guys, right? I could use the entries from the second row or the third row or the first column or the second column or the third column. You can use any row or any column for these first factor in those products. Okay. All have to be in the same row or column, yeah. But you can use any one you want. Yep. Yes, but these submatrices have to correspond to the matrix you get when you delete the same row and column as are written there, right? Yeah, so any row, any column, as long as, I should say, as long as the first factor of each term, oh, sorry, so long as when the factor you use from the row or column you choose corresponds to the determinant of the same capital A with that row and column deleted. So this is called the cofactor expansion across a row or down a column. It can save you a lot of time if you happen to have a row or column of A that has a lot of zeros in it, because then whenever these guys are 0, the whole term drops out. The signs still alternate, but it doesn't always start with a positive. Okay, so if the row or the column number you're expanding over is odd, you start with a positive. So up here, when I expanded over the first row, I started with a positive because 1 is odd. Okay, if you start with a row or column, if you're using a row or a column that's even to expand over, you start with a negative. So we'll do an example of each in the demo. That same method generalizes to n by n matrices, not just for 3 by 3. Just continue using the entries from your chosen row or column as the first factor of each term until you run out of entries. The signs still alternate, same rule. Row or column number you're expanding over is odd, start positive, even, start negative. So if you had an n by n matrix, you'd be adding n terms total. In this example, I had a 3 by 3, and I had 3 terms. 1, 2, 3 terms. 1 for each entry from the row or column you're using. And then an alternate notation for the determinant of A is like absolute value bars around the matrix instead of brackets. So we have the determinant of A Same thing as the determinant of A. Same thing as, looks like absolute value, but we'll read that determinant of A. No, you start with a positive or negative based on which row or column you're expanding over. So in this example, I expanded over row 1. Those were the coefficients I used here. Row 1 is odd, so I started with a positive. If I had expanded over column 2, if I had used those as my coefficients, I would have started with a negative because 2 is even. Okay, so here's an example. I've got a 3 by 3 matrix. I want to calculate the determinant. I know that this is the determinant because I don't have these little brackety guys on here. It's just 2 vertical lines. Yeah. So this says calculate the determinant of that matrix using a cofactor expansion across the first row. Okay, so I'm going to use my first row here. Those are going to be my coefficients, the first term of everything. So my determinant of that matrix A, I'll just call that A. My first term is going to be positive because I'm using row 1. 1 is odd. I start with a positive. So this is going to be 1 times the determinant of the matrix I get when I delete the row and column that 1 is in. So the matrix that remains is 1, 1, 4, 2. Okay, so my next term of row 1 is a 3. Alternate my sign, so I have a negative now. What matrix remains when I delete the row and the column that the 3 is in? 2, 1, 3, 2. And then I switch to a plus. The next term in the first row, the next entry in the first row is a 5. So I have a 5 times the matrix that remains when you eliminate the row and the column that 5 is in. 2, 1, 3, 4. No, because these mean the determinant of the remaining bracket of the remaining matrix. And then now these are just 2 by 2 matrices, and I can calculate their determinants by using AD minus BC. Right? So I would do 1 times 2 minus 1 times 4 minus 3 times 2 times 2 minus 1 times 3 plus 5 times the determinant of 2, 1, 3, 4 AD minus BC. Oops. All right, so that's negative 2. 4 minus 3 is 1, so that's negative 3. 2 times 4 is 8, minus 3 is 5, times 5 is 25. And that ends up being 20. Not quite so bad, right? Once you do an example. 1 times 3, sorry. So this is the cofactor expansion across the first row. Right. So if I'm going to use the second column, that just means that instead of using this guy and this guy and this guy, I'm going to use the entries down the second column. No, you only have to do 1 to get the determinant. They'll all give you the same answer. Yeah, so you can use whichever one is most convenient. I just am doing it 2 ways to demonstrate to you that they come out the same. All right, so here I'm going to do the exact same problem. It should come out to 20 because we already know the determinant is 20. We just calculated it. We're just going to do it a different way now. So I'm going to calculate the determinant of my matrix. This time I'm going down the second column instead of across the first row. Column 2. 2 is even, which means I should start with a negative. Negative. And my first entry is a 3. And then the matrix that remains when I eliminate that 3 is 2, 1, 3, 2. And now I alternate my signs. I started with a negative, so my next sign is positive. Because I was using an even column. Right, I'm using column 2. 2 is even, start with a negative. If your row or column number is odd, you start with a positive. Even, start with a negative. So you can expand over any row or any column, right? If you choose an odd numbered row or an odd numbered column, like 1 or 3 or 5, right? Up here, I started with row 1. 1 was odd, so I started with a positive. The odd numbered row or column, start with a positive. Even numbered row or column, you start with a negative. So the negative didn't come from anywhere in here. It came from the rule. Yep. Okay, so I start with a negative. The first entry of the second column is a 3. These are the remaining numbers when you eliminate the row and column that contain that 3. Okay, next entry in column 2 is a 1. What numbers remain when you eliminate the row and column that contains that 1? 1, 5, 3, 2. And then I go minus. The last entry of column 2 is a 4. And when I eliminate the row and column that contains that 4, I'm left with 1, 5, 2, 1. And now I just have a bunch of 2 by 2 determinants to calculate. So this is going to be negative 3 times 4 minus 3 plus 1 times 2 minus 15 minus 4 times 1 minus 10. So that's negative 3 minus 13, right? Yep, okay, and then 1 minus 10 is negative 9 times 4 is 36. Negative 26 plus, oops, it's not 26. Negative 16 plus 36 is 20. So you get 20 this way also. So because you have your choice of what column and row to use, if you have a row or column that has a lot of zeros in it, choose that one, right? Because then you don't have to actually calculate the determinants of these submatrices. So here's a big one. We've got a 4 by 4 matrix. I want to find its determinant. I can use a cofactor expansion of my choice, which means I can choose any row and any column. Row 3 or column 4. Yeah, probably row 3 is easier because it's got a 1 in it as opposed to a 2. So I'm going to use row 3. I'm going to go across row 3. So my first entry is a 0. I don't even care what the submatrix is. I'm not even going to bother trying to figure it out because I'm going to do 0 times whatever that determinant is will be 0. Plus 1 times the submatrix that I get when I eliminate the column and the row that contain that 1. So that submatrix is negative 1, 4, 0, 2, 3, 2, and 0, 2, 0. You would have to tell the person what you were doing. There's no convention. Yeah, no. Okay, my next 2 terms in row 3 are, oh, that is a minus. Thank you. Yep. I forgot about the sign alternating thing. Yeah. So we're using row 3, which means start with a positive, right? So that's positive. And then I switch to a negative to alternate the signs. Okay, and then I have positive 0 times something minus 0 times some submatrix. Don't even care what they are. All right, so the next thing I have to do is I just have to calculate -1 times the determinant of this matrix. And to find the determinant of that matrix, I'm going to have to use a cofactor expansion across any row or column that I want. Which one do you want to use? Row 3. It's got 2 zeros in it. Okay, so I've got -1 times. Yeah, because within finding the determinant of A, I have to find the determinant of this 3 by 3. Yeah. Right. Yeah. If you have a really big matrix, you're going to have to do this several times as you work your way towards the answer. Okay, so I'm using row 3. 3 is odd, which means I start with a positive. So this is going to be 0 times a submatrix, I don't care what it is, plus 2 times a submatrix that I get when I eliminate that column and that row. So that leaves me with -1, 4, 0, 2. That's a -2. Oh, yep, you're right. Yep. You are right. This is a -2. Yeah, I started with a positive, moved to a negative. And then my last term is 0 times some submatrix. 0 is the last term of row 3. All right, so nope, this is in some submatrix. I just don't care what's actually in there because I'm going to multiply it by a 0. Same thing here. I just didn't even bother writing it down. -1, 0, 4, 2. Oh, yeah, it would be the same coefficients, but yeah, I'm using row 3. Yeah, it's okay. Yeah, I should mark that. I'm using this row as my coefficients. Okay, so I've got -1 times -2 times the determinant of this 2 by 2 matrix, which is -2 minus 0, AD minus BC. So I have -1, -2 times -2 is +4. Determinant is -4.